Okay, so today we will continue with conservation laws. If you remember, on Monday we had discussed the conservation of momentum. So we had not momentum, of energy. Now the problem with the conservation of energy was, if you remember from mechanics courses, it was kind of quite easy to identify what the energy of a particle is. If you remember, we had this kinetic energy work theorem, which kind of suggests the definition of the kinetic energy. And if we have conservative forces, we could write the work done by that conservative force as the change in the potential. And again, the work energy theorem suggested already the definition of the mechanical energy, which we defined as the kinetic plus the potential energy. But in electromagnetism, we have 4 different equations. We don't have these point-like objects, so we cannot really say that the energy is 1/2 mv², or the momentum is mass times the velocity. But nevertheless, we would like to prove, we always use the energy and momentum conservation in our everyday life. And if you consider what the forces are in our everyday life, they are all electromagnetic forces. There is no other force that we feel in everyday life except the gravitational attraction of Earth. You see, the friction is an electromagnetic force. It comes from the electromagnetic interactions between surfaces. Pull and the push forces are have electromagnetic forces as their origin. So if electromagnetic forces did not conserve momentum, then definitely we should have seen some effects of momentum, of that non-conservation, but we don't. So we can strongly believe, we can have this intuition that energy and momentum should be conserved. But of course, we need to identify what is the expression of the energy and what is the expression of momentum for our particles, for the electromagnetic waves. And if you remember, when we were looking at the conservation of energy, we started with the mechanical energy of the system, which you can just write as sum over all the particles, 1/2 the mass times the velocity squared, plus the potential energy for the ith particle. Ui is the potential energy, any potential energy that is not due to electromagnetic forces. For example, gravitational potential energy is over there. But that potential energy is, we don't take the potential energy, if we can define any, corresponding to the electromagnetic forces, because we basically don't know what the energy stored in electromagnetic forces, but we know the forces themselves. So we said that, okay, the rate of change of the mechanical energy, and if you remember work energy theorem, the work energy theorem told us that if you have in the mechanical energy, you add you describe some forces, you already take into account some forces through their potential, but there might be other forces acting on the system, and the rate of change of the mechanical energy should be equal to the work done by the other forces. In this case, it's the electromagnetic force that exists in the system. And so this should be equal to the work done per unit time. So this is the power delivered to my system by the electromagnetic forces. And we had seen that if we make this this is from mechanics, and because of this, we already know the force acting due to the electromagnetic forces, and so the power would be just the Q rho, no, not rho, sorry. It's E dot J, integrated over all the volume to take into account all the forces acting on all the particles. And we had seen that this we could write as minus d by dt of some function, some scalar function, minus the volume integral of some vector. Sorry, the area surface integral of some vector. And then we said that d by dt of u mechanical plus ue electromagnetic is equal to minus s dot dA. So this was the result we obtained, and then we could interpret this result as, well, we already know what the mechanical energy is. This is the energy stored in the electromagnetic fields. It only depends on the electromagnetic fields in my system. This was equal to some volume integral of 1 over 2 epsilon 0 E squared plus 1 over 2 mu 0 B squared. So this is what we call the energy stored in the electromagnetic fields. Then we have this term. And that term we also interpreted in this form. You see, this U mechanical energy is the mechanical energy of the particles within my volume V. Let's say this is V. This is the electromagnetic energy stored within my volume V. Now, what does conservation mean? In the strict sense, if something is conserved, its total in the universe doesn't change with time. But that definition is also not so enough for us, because you see, if something disappears here and appears in the Andromeda galaxy, it's also conserved. But we know that if something disappears here, it's because it just moved slightly to one direction. So that is what we understand from conservation. If we have a volume, if something changes within that volume, if that thing is conserved, that can only be because some of it just went out of my volume, through the surface of my volume. So that is how we interpret this term over here. So this is the total energy stored in my volume. That energy can be changing. It can change with time. But if it changes with time, it means some of the energy flew out of my volume, through the surface of my volume. And it is this term. So this S, what we call the Poynting's vector, describes how energy flows through the surface. And if I'm not wrong, S was equal to 1 over epsilon 0 E cross B. Can you check it? Did I? Mu 0. Okay. So this was the flow of energy. So that is basically where we had left. Any questions up to this point?
Pointing vector neural.
It's the flow of energy. The energy is just, if my system is changing in time, you see, I have all these charged objects around. If those charged objects are moving around, they will create a magnetic field, B field. But if they are moving around, it means the energy and the magnetic field, either both of them or some of them, they will be changing at every point. So we know that energy and the magnetic field, they carry energy. Electric field and magnetic field, they carry energy. So if they are changing at a point, that means energy density at that point is changing. But that means energy is moving around. And that motion, that flow, is described by the Poynting's vector. You see, we had defined, for example, the current. Current is the flow of charges. Or the current density was the flow of charges per unit area, etc., per unit time. Poynting vector is the same thing, but for the energy. It's the flow of energy per unit area, per unit time.
Enerji bir vektör değil.
And
Enerji bir vektör.
charge is not a vector, but current is a vector. Because current moves in a direction. That is what is creating the flow. Similarly, energy, you're right, energy is not a vector, but it can flow in a direction. So that flow is a vector because it has a magnitude and a direction. So this is what we call the Poynting's vector. Well, we will basically repeat the same strategy, let's say, for the case of the momentum conservation. You see, we will be deriving completely different conservation laws. The expressions will be looking completely different. but our strategy will be exactly the same. You see, what was our strategy here? We looked at the change in the mechanical energy of the system because that is something we are familiar with. We already know from the mechanics courses what the mechanical energy of point objects are. So that is something we know. We started from something we know. And we looked at how that changes. And then, starting from that, we obtained a relation which was, again, the time change of something else and some surface integral. So in the case of momentum, we should basically do the same thing. We should start from something that we know. I mean, if you start from something that you don't know, there is nothing much you can do. We should start from something that we know. We know the mechanical momentum of point charges. Then look at how it changes with time. Well, the rate of change of momentum is nothing but the force. Force is created by the acted on our charged objects due to the electromagnetic fields in our system. That's the Lorentz force. And we will try to write that force as the time derivative of something else, which we will identify as the momentum of electromagnetic fields, plus some surface integral, which we will interpret as the flow of momentum through a given surface. But that is also kind of interesting. You see, you have a surface, there is some momentum hitting that surface, let's say, and if there is nothing there, it's just passing through. So there is a surface, there is a momentum hitting that surface. What is the force per unit area? Momentum, well, if there is a momentum flow, there is a force acting on that surface, and the force per unit area is pressure. So through this procedure, we will also be able to identify the pressure exerted by electromagnetic waves. Yeah, it's not a great surprise that electromagnetic waves exert pressure. Basically, everything is made of charged objects. So if they are interacting, so the charged object will feel a force, and hence there will be a pressure acting on any given surface. That's also something we will be able to identify. Now let's first try to guess. One problem that I see when you are trying to solve a given problem is that you don't think about a strategy. You just try to just do equations after equations after equations and hope that you get an answer eventually. So I would suggest you all the time first determine your strategy. What will be your steps? I mean, your steps can be complicated. You can do mistakes, etc. But I mean, if you make a mistake, you just go over them again. You find it, you correct it, etc. But without a strategy, you are kind of lost. Well, the same holds for me, for anybody, for the lecture. So what should be our strategy? One thing, we had already determined our strategy. Look for the rate of change of the mechanical momentum. Try to express it as the rate of change of something else, which we will identify as the electromagnetic momentum, plus some surface integral. Okay, that is one strategy. What might the answer look like? What might the momentum look like? You see, in the case of energy, we already had some idea about what the energy of an electromagnetic field should be. This term we are already familiar with from when we were looking at capacitors or the energy stored in an electric field. We already discussed in electrostatics. It already looks like that one. Now we know that it is also valid in electrodynamics, not only in electrostatics. When we were looking at the solenoids, we had seen that the energy stored in a solenoid can be written in this form. In that case, we had seen that that expression is valid in magnetostatics, but now we know that it is valid also in electrodynamics. And we had that additional term which we interpreted as the flow of energy. Now, we don't have any experience about the momentum. What can be the momentum of electromagnetic fields? So let's try to understand what momentum of mechanical systems are. So what is the momentum of a mechanical system of a point mass? Mass times velocity. Okay, that is how we define the momentum of point objects, point masses. Well, of course, this interpretation of momentum doesn't really tell us much because we cannot use it in electromagnetism. There's no mass over there. We cannot really identify a velocity, at least not yet. So we cannot really use it. So how else can we describe this? The force over time. Over which time? Well, you see, we will be using this one. We will be using this one anyway. So that will be our starting point of the rigorous derivation. Let's try to guess what the answer might look like. So how else can we interpret this? Not necessarily in terms of equations.
Minus D, P electromagnetic radiator.
Okay, that is, we don't know what the P electromagnetic is yet. Okay, we had determined our strategy. Now let's try to identify what the answer might look like. Okay, P electromagnetic, fine, that's our strategy. So we are trying to obtain an expression of this form. That's what we will try to do. We will try to convert this equation over here to an expression of that form. That's what we will do later on, but can we guess what might it look like? So let's forget about electromagnetism first. I have a mass over here, and it's moving with some velocity v. And then the mechanical momentum is m times v. What is the energy in this system? Energy is equal to 1 over 2 mv squared. Let's ignore the potential for the time being, any kind of potential. Where is the energy? It's the energy of the mass. The energy is over here. Let's look at a later time. So initially it was here. And now it will be somewhere over here. Now, it still has the same energy if there are no external forces. But where is the energy now? Exactly. It's at the position of the mass. But the position of the mass has moved. So energy has flowed in the system due to the momentum of the system. So another interpretation of momentum is related with the flow of energy. But we already know what the flow of energy of the electromagnetic field is. What describes the flow of energy in the electromagnetic field? Pointing vector. So if, in this interpretation of momentum, at least, it is related with the flow of energy in my system. And the flow of energy, we already know that it is given by the pointing vector. So the momentum of the electromagnetic field, we expect it to be somehow related with the pointing vector. So that is at least something to look for in our equations. Well, another way of interpreting, looking at the flow of energy or relating with momentum with energy is just think about the Einstein's equations. So let's say electromagnetic fields, they do not have a mass, but we can still describe an effective mass because they have energy. Mass would be E over c squared. We will see later on that electromagnetic changes in our system, they move with the speed of light. So the velocity, the speed of electromagnetic fields, at least the flow speed, will be more, we can identify it with c squared, the c.
Hocam, is it about 4 vector? Is it about 4
No.
vector?
I'm not even mentioning 4 vectors. Energy is, and this is the, it will be flow, it will be, energy is the flow of energy is the pointing vector, and again here we should somehow get the pointing vector. This is just kind of another argument. Now let's try to make it more rigorous. Okay, this is our claims. So we had determined our strategy. We will start with this equation over here. We know what the force is. We will try to convert it into this form. And what we are expecting is somehow this, what replaces this in the case of the momentum conservation, it should be somehow related with the pointing vector. So that also tells us, hints, guides us, let's say, which kind of manipulation we should use. Shall we proceed? Or questions? Okay, so we identified our strategy. So if you agree with our strategy, if you think that it might work, so we can just proceed and do it rigorously. Well, of course, there will be some complications, some differences. I mean, before we did this procedure for the energy, which is just a number. Now we are doing it for momentum. Well, momentum has 3 components.
Into the pointing vector is energy of that.
Well, let's see, what is the unit? If we did everything properly, the unit of that integral over here, the unit of this integral should be energy over time. Well, the unit of this one, this integral, is the unit of the pointing vector multiplied by the area. So the unit of pointing vector should be energy per unit time per unit area. Well, if you compare it with the unit of the current density, you see current density was charge passing through passing through a given area, that's charge per area, per unit time. So this one is energy per unit area per unit time. Well, that will be your first homework, let's say. What's the unit of that expression? We know that it should be energy per unit area per unit time, but just put in the expression of the energy, electric field, expression of the unit of the magnetic field, divide by the unit of mu0. It should give you energy per unit area per unit time. If it doesn't, that means we had done something wrong. Now, we know that the conservation of momentum, all 3 components should be conserved, not just one component. So let's look at any one component. It can be the conservation of the x component of momentum, y component, or z component. We had seen that this should be equal to, that's what our strategy is, minus, we should identify the linear momentum of the electromagnetic field, then take the I component of it by dt, minus some surface integral, some area integral. Well, this is a closed area. For each component, for the x component, for the y component, for the z component, there should be a vector over there. So we have a vector for the I component. So Ti is a vector for I is equal to x, y, or z.
Burada anlamadım hocam. Şimdi Geçen de hani konuşmuştuk. Double vektör demiştiniz. Yani çift yönü mü var? Hani double vektör.
Now you can say that, okay, it has double directions. Double direction in the sense, if you remember, we also described the waves on strings. Let's say we have such a wave moving on a string in this direction. So what is the motion of the masses making my string? They're just moving up and down. This is, at this instant, it's moving down. And at this point, at this instant, that point is moving up. So we can talk about the vertical momentum. Let's say this is the x, this is the y direction. So we can plot py as a function of x at a given time, at this time. So here, there is no momentum up to this point. They are at rest. After this point, there is no momentum. Well, these particles are moving in the minus y direction, so at this point, there is a negative momentum. The momentum becomes negative. And then at this point, it's at the maximum point, it's neither moving up nor down. At this instant, it is at rest, so the linear momentum is 0. To the right of it, the linear momentum is positive linear momentum in the y direction. So this is what the momentum looks like in this wave. Probably this should be steeper, and this part should be steeper, but nevertheless, the basic idea is the momentum is negative here, is positive here, and this is the py. It's the y component of the momentum in the vertical direction. But this is also a wave moving in the x direction. So as the wave is moving, this will also move with the wave. So I have there is a y momentum distribution which is moving in the x direction. So that is why we have two directions. The component, one is the direction of the momentum. The other direction is the direction of the flow of momentum component. So that's why it has two directions.
Ama hani öyle düşünün. Çok basit düşündüğümde iki tane vektör, iki yönlü bir vektörüm var. Niye bunların bileşkesi?
It's not the sum of those two vectors, neither the product of those two vectors. It's a completely different object. You see, if you look at a scalar is an object which doesn't have any direction information. A vector is an object which has a single direction information. You can say it's a tensor of second rank, or sometimes it's also called dyadic. It's an object that has two direction information. It's not the sum of those two vectors. So, for example, it will tell me in which direction the y component of momentum is flowing. In the case of mechanical point-like objects, the direction of the flow of momentum is simply the direction of momentum. It was kind of easy. But when we have waves, in this case electromagnetic fields, that correspondence is lost. So the y component of momentum, as in this example, it need not flow in the y direction. It will be flowing in the x direction. Well, the y component of momentum is also flowing in the y direction in this case. Because you see, initially, at this instant, at this point, there is no linear momentum in the y direction. At the next instant, when the string is lifted up, at this point, there is a y momentum. There is a momentum in the y direction. So the momentum in the y direction is flowing both in the x direction and also in the y direction. And this quantity over here basically does the same thing. It describes the same thing for the electromagnetic fields. We will identify the x, y, and z component of the momentum of the electromagnetic fields, but that component, let's say the x component, need not flow only in the x direction. It can be flowing in the x direction, also in the y direction, and also in the z direction. Now let's try to derive it. And well, of course, this, for the time being, we are assuming that we can find such a relation. We have a, let's say, belief that such a relation should exist. That is our hint. That's our hunch. But I mean, just a hunch, just a belief would not be enough. We have to prove that it is so. And to obtain that relation, we again use the Maxwell's equation plus the Lorentz force acting on charged objects. Now let's go back. This is our starting point. This is something we know. This will be equal to the I component of the force. It will be the x, the y, or the z component. Well, this force is, you can write it as, if you want, as a sum qi, the electric field at that point, let's call it EI, plus VI, times the magnetic field at that point. Or we can convert it to an integral. This will be equal to the volume integral of rho times E. Well, Q times the velocity is nothing but the current density plus J cross B. Of course, we are looking at the I component. Now, of course, I don't want to, I want to convert this to an expression which will only involve the electromagnetic field. It shouldn't depend on the rho and the J. If I want to identify the energy stored in an electromagnetic field, well, it should be independent of any possible charges in the region. So the first thing I have to do is replace these densities and currents in terms of my fields. What will be my fields? Let's again remember the Maxwell's equations. We have the del dot E is equal to rho over epsilon 0 in vacuum. Curl of E is equal to minus dB by dt. Del dot B is equal to 0. By the way, I also suggest you to write the Maxwell's equations in every opportunity you get so that you remember them. And the curl of B is equal to mu 0 J plus mu 0 epsilon 0 dE by dt. So we can solve for rho. Rho is equal to epsilon 0 times the divergence of E. And J is equal to 1 over mu 0 curl of B minus epsilon 0 dE by dt. So I will just replace these in my equations over there. dV E times rho. Well, rho is epsilon 0 times the divergence of the electric field plus J is 1 over mu 0 curl of B minus epsilon 0 dE by dt cross B. Well, this much is not enough. I mean, we have to kind of simplify it and convert it to a form that we are looking for. You see, what the form that we are looking for is this one. It should be some time derivative of an object plus a surface area integral, surface integral. And of course the I component. Well, we already have one time derivative over there, this one. We can convert it to a total time derivative, which I can take out of the integral. So let's try to do that. We have this expression dE by dt cross B. This is equal to d by dt of E cross B. Well, if I take the time derivative of this cross product, I get the derivative of the energy, electric field, cross with B. It is this term over there. But I also get the electric field cross the time derivative of B. So if I want to keep the equality, I have to subtract that additional term. Well, you see, we already have this one over here. E cross B is our pointing vector. So that is kind of what we were expecting. We were expecting the momentum of the electromagnetic field to be related with the pointing vector. So this is that part over here. But this doesn't seem to have helped much because here we already had that time derivative. This term has an overall time derivative, but not that term. But keep in mind, this time derivative we can write in terms of an expression that doesn't involve the time derivative. The time derivative of B is nothing but the curl of E. So this is equal to del by del T E cross B plus E cross curl of E. So we have a term that has that partially time derivative. It has a part that has the time derivative. We can write this term as a part which is the time derivative of the full expression, not just part of it, plus a term that doesn't depend on our current densities, our charge densities, neither the time derivative. So let's just put it over there. We have the Tp mechanical, the I component divided by dt. Well, you see that term was basically this term over here. This is equal to minus epsilon 0 over mu 0 sorry, this is mu 0 epsilon 0. I made a mistake over, this is epsilon 0 over here. So there's no such parentheses. If I put it in a parenthesis, I should insert a mu 0 over here. That was a mistake. So we have minus mu 0 epsilon 0 times the total time derivative of the volume integral of E cross B over mu 0. Okay, this is only that term. I took that term, I will write all the rest, and it is this term coming from that term over there. Okay, so this is kind of what I already expected. I already have the total time derivative of the total mechanical momentum of my system is minus the total time derivative of something else. That something else I can easily identify as the linear momentum of the electromagnetic field. Let me put the I. I'm looking at the I components for the time being. But then I have all the other terms. So let me write all the other terms. Plus, I have this volume integral. What I have, again from the same term, from the dE by dt cross B term, I have this part, curl of, E cross the curl of E. And the overall coefficient is minus epsilon 0. So this is the first term. This is one of the terms that I'm missing. I have the plus 1 over mu 0. You see this term over here, 1 over mu 0 of curl of B cross B. Okay, this is, well, if you just look at these terms, they look quite symmetric. The only thing I need to do is, if I exchange the position of the vectors in this cross product, they have the same sign. Well, the role of epsilon 0 in electromagnetism is similar to the role of 1 of mu 0 in magnetism. This is electrostatics, this is magnetostatics, let's say. So they look quite symmetrical.
Cross product nerede? E'deki cross product nerede?
Which one? You see, we had this term, du by dt cross B, right? What we did was we wrote this as the total time derivative of E cross B minus E cross dB by B dt. But this dB by dt is nothing but minus the curl of E, Maxwell's equation. So that is why we have the second curl of E. Any other questions before you go for a break? After the break, we will continue. You can still ask questions. Not yet. Our expression is not yet complete. There are additional terms that we have to write. Let's write them, and then you go for a break. Okay, so what did we write? We wrote all of this term. We wrote this term. The first term we didn't write. Let's add that term also. Plus epsilon 0 E times the divergence of E. I will take the I component of this thing. Well, you see, the first line is quite symmetrical, but the second line we have a term that contains the electric field, but we don't have the term that contains the magnetic field. Well, that is not that nice, but we can correct it. Let's add that term. I mean, you see, if everything were symmetrical, then we would have this term, 1 over mu 0, B times the divergence of B. So if we add that term, things look quite symmetrical between the electric and magnetic field. I mean, you see, Maxwell's equations, they already look quite symmetrical between the electric and magnetic field, the main difference being that there are no magnetic charges, although we have electric charges. That's something that is not so symmetrical or good-looking in Maxwell's equations. But besides that, everything is between the electric and magnetic field. They are very much symmetrical. If we add this term, again, this integral also looks quite symmetrical. Well, you see here, this also looks quite symmetrical between E and B. This second term in our expression looks symmetrical. If we add this term, what is the value of this term? It is 0. So we are basically adding 0. We can easily do that, and we will do that. So we are just adding that term. So the thing that is left to do, okay, that term is something we like. I will identify the electromagnetic momentum as equal to mu 0 times epsilon 0 times S. And just keep in mind, we will derive it later on. Mu0 times epsilon 0 is basically 1 over c squared. So it's kind of the energy flow divided by the velocity squared. So the P mechanical, let's say the I component, so the rate of change of P mechanical, the I component, well, this is a volume integral, plus the I component of the electromagnetic momentum is now equal to this volume integral. Well, there is one thing left to show, that this volume integral is actually the volume integral of the divergence of something. So we need to show that this is actually the divergence of this quantity, and we have to find what that quantity is. So that is what we will do in the next hour. So at least part of the derivation is already complete. If we can find, if it is still an if we can find such a vector field, then we will definitely say that what we wrote above, this integral mu0 epsilon 0 s, is the linear momentum density. If we integrate it over the volume, it is the linear momentum of the electromagnetic field. And so that the linear momentum of the electromagnetic field plus the linear momentum of the point charges, if there are any in motion, that is a conserved quantity. Well, we cannot say linear angular momentum, but we will see angular momentum. We will define the angular momentum. Well, I don't think we will derive the conservation of the angular momentum, but linear momentum is conserved, angular momentum will be also conserved.
Hocam bir şey soracağım. Şimdi biz bir sistemi incelerken hani enerji korunuyor mu diye bakıyoruz. Sonra momentum korunuyor mu diye bakıyoruz. Bazen bunların ikisi korunmuyor ama açısal momentum korunuyor. Peki açısal momentum da korunmazsa ne oluyor?
So what are the conditions? You see, you should be also whenever you derive a result, that result is valid under certain conditions. Now, if you remember our mechanics courses, we said that linear momentum of a system is conserved if there are no external forces. So linear momentum of a system can change if there are external forces. Of course, external forces are exerted by some other object in the system. And if there are some other, we have our system, there are other objects, we can also define our system as the whole thing. In that case, the linear momentum of, if there are no external forces now, then linear momentum will be conserved. So the same holds for, okay, let's see, the linear momentum is conserved. The same holds for energy. The same holds for angular momentum. The angular momentum is conserved if there are no external torques acting on the system. So what are the torques that can act on our system? You see, here when we are looking at mechanical systems, in real life, for example, I'm considering this one. What are the forces acting on this one? There is all the charge distribution of the electrons and the nuclei, protons and neutrons. Those are the charges I have. They have some mechanical momentum. Let's say at this instant they are at rest. No, not they are not at rest, but overall the system is at rest. So the linear momentum is 0. The interaction between all the atoms are electromagnetic. So the linear momentum of this system is actually the linear momentum of the atoms plus the electromagnetic field in my system. Now if I release this, if I release my finger, allow it to rotate, well, the linear momentum is no longer conserved of this keyboard. Why? There's gravity, our external force. And since I define this as my system, not my hand, there is a force exerted by my hand. This is an external to my system, so linear momentum of this system is not conserved. Angular momentum with respect to this axis, is it conserved? No, it's not conserved because there's an external torque on my system. And the external torque is created by Earth due to gravitational interaction, not even electromagnetic interactions. The torque, so since there is a torque acting on the system, the angular momentum is not conserved. But if I would take this to space, the total angular momentum will be conserved. You see, at this instant I'm saying that linear momentum is conserved, it is constant. But the atoms making this are just moving randomly. At one instant, an electron is moving in that direction. At the next instant, it's moving in the other direction. So the linear momentum of a single electron or a single nucleus is not conserved in time. It is constantly changing. But it's changing due to its electromagnetic interactions with other electrons and nuclei. And the linear momentum of the electrons are changing, the nuclei are changing, electromagnetic field is changing constantly in the system. But if there are no external forces, no net external force, like if I'm holding it like this, the net external force acting on my system, the keyboard, is 0. There are no external force, so no matter how complicated the interaction, the electromagnetic interaction of the charges making my system are, the total linear momentum is conserved. That is basically our proof over here. So, of course, you see, here we are not making an assumption on our system. We are just saying that we have a bunch of charges. Well, if you want, just add the neutral objects also. We have a bunch of point masses. Some of them might be charged, some of them might be neutral. There are electromagnetic forces acting on them. Well, these electromagnetic forces might be due to the other charges in the system, or might be due to some other charges that's not in my system. So, since we are talking about conservation, we should rather take into account all the charges, all the particles that are feeling any forces or exerting any forces. So we have these bunch of objects which might be feeling electromagnetic force if they are charged, or they don't feel electromagnetic force if they are neutral. And they are moving under the influence of this electromagnetic force, then the total momentum of our system is conserved. The total linear momentum, meaning the linear momentum of my point masses and the linear momentum of the electromagnetic field. This is nothing but a bunch of charges interacting electromagnetically.
Şimdi hocam biz bu cisme baktığımızda şeklini böyle görüyoruz ya, işte köşesi falan var. Aslında hepsi tamamen atomlardan oluşuyor.
Correct.
Yani sisteme dışarıdan bir atom girdiğinde bu cisimden dışarı başka bir atom fırlayabiliyor mudur acaba? Yani aslında şekli tam böyle belli
Well,
değil.
may I take your pencil? I will not do it, but let's say if I push it strong enough, will there be something getting out? I will not try it with my keyboard, of course, but I mean, you can punch holes through things, right? So you're not sending just one atom, you are sending many atoms. You are changing the shape, though. You can make holes if you want, but of course it won't work properly in the way that you want it to work afterwards, but you can do it. Or you can just make a single mark over here with your pencil, write on it. That is basically a transfer of atoms. You are adding atoms, which is not really making a significant change in its function, neither its shape. Then why do we see it black? Now that is something we will discuss, by the way. It's just how it interacts with electromagnetic radiation. Light. So if you send light, we see it this black because this object, the way it interacts with the light part, that you send on it, it just absorbs everything. That light is converted into the mechanical energy. The energy stored in light is converted into mechanical energy of this keyboard. So the keyboard gets warmer if you shine light on it. Well, the difference will be very small. You will not actually feel it unless you just set it under the sun for a long time. You won't be feeling the change, but that's actually what's happening. The light is absorbed by the keyboard, so there's no light coming to us. So our brains interpret it as black. Okay, go for a break, and then we can discuss. You have 10 minutes.